Hello there, and welcome back. Today we're going to continue our exploration of the R programming language and focus on how to solve a variety of different types of equations in a different number of circumstances. If that's not your goal, but you're still trying to get more comfortable with the R language, this video definitely will go through several different things such as function creations, plotting, and a couple other little graphical details associated with it. With that being said, let's get started. One of the types of equations that you'll definitely have to deal with is where you have several different variables and they all need to satisfy a series of different constraints. So the easiest type of setup that you would have is a systems of equations where you have, for example, three unknowns and three equations. And let's just assume that that is the problem that we're going to be looking at. In particular, how to solve square systems of equations. So let's just give a quick example. Let's assume we want to solve 3x minus 7y is equal to 9 and 2x plus 5y is equal to 10. So what value of x and y will satisfy both of these equations simultaneously? That's the question we want to answer. So the very first thing that you probably want to do is create two different matrices, or in some sense, one matrix, one vector. The first matrix that you want to create is the coefficient matrix of 3, minus 7, 2, and 5. And make sure that you have x's in the first column, y's in the second column. So what we're going to do is we're going to create two rows and then we're going to bind those rows together. So we're going to bind the first row, which is going to be 3 minus 7, and then the second row, which is going to be equal to 2 and 5. Okay, so once we do that, we can see it over here in our R environment, but if that doesn't sort of help you visualize what we're looking at, if you just type A and then represent that, it should give you the coefficients 3, minus 7, 2, and 5. So we have our column 3 and 2 for our x's and minus 7 and 5 for our y's. So our coefficient matrix A is correct. And then the next thing I want to do is create my coefficient vector, which is going to be 9 on row 1 and 10 in row 2. And that's going to be equal to an R bind of, again, two vectors, C9 and C10, right? So 9 is the first row, 10 is the second row, both of unidimensions, right? If that doesn't help you visualize it, it should be 9 and 10 in that sense. And keep in mind this has to be a matrix, and this should be a column vector. So once you have your A and B selected, now we're ready to solve the systems of equations, provided that it does have a solution. So one way you can test to see if it does have a solution is to take the determinant of that coefficient matrix. So you can take determinants in base R with DET, and as long as this number is not equal to 0, this square system will have a unique solution. And I'm not going to get into the theory there, but if you're interested, linear algebra is the place to search. And keep in mind, you won't be able to do the determinants of non-square matrices. That's another downside of this as well, right? But if you do have a square matrix like we have, you can do the determinant to check and see if you have a unique solution. As long as it's not equal to 0, it has a unique solution, and you can find it in base R by doing solve A. That will do the inverse of that matrix, and then percent star percent will do matrix multiplication with B, and that will give you the solution of your system. So if you substitute 3.96 for x and 0.41 for y in both of these equations, you should get approximately 9 and 10, respectively, for both of those equations, and therefore this is the numerical solution to that particular matrix equation. The next problem we want to look at is one that several of you are probably already familiar with, at least in the basic sense, and that's solving equations of one variable, particularly on some interval, especially if you have infinitely many solutions. In case you don't already know, several equations do not have solutions that are easily representable in terms of functions that you probably are aware of, like natural logs, exponentials, sine, cosine, and several many others. So sometimes numerical solutions is the best you can get. So let's assume we have this equation, 3x cubed plus e to the minus x is equal to 13. And we want to find whatever solutions that belong to the interval 0 to 2 that solve this particular equation to hopefully some decimal place accuracy. The more the better, of course. So the first thing that we need to do in this particular scenario is to set this equation equal to 0. So if I do that, I'm going to have 3x cubed plus e to the minus x minus 13 is equal to 0. And this function is what I am going to call f of x. All right, so this is sort of how our functions that are going to solve this are going to be implementing these solution strategies. So let's define our function f. So f is going to be a function of one variable x, open close brace there, and our function is going to be equal to 7 times x cubed plus, keep in mind there's no e to the power, e is a letter in the realm of r, so we can do exp of minus x, and then we have minus 13. So that is f of x. Right, so let's just give that a run. So we have f defined over here. So for example, if we do f of 2, that's what you will get if we plug 2 into that particular equation. So that's pretty much how functions work. Let's get an idea of how many solutions we have for this function by actually constructing a graph of what this function looks like. So let's create a curve. Let's use the curve function for graphing, and let's do f of x, and let's plot on the interval 0 to 2, and let's color this curve, let's say steel blue. I think it's a pretty color. So once we give that a run, that is going to give us the graph of this function, f of x, defined on the interval 0 to 2. And we want to know when this function is equal to 0, because that's when the left-hand side of the original is equal to 13. That's pretty much what we're doing here. So let's just draw a horizontal line here to sort of get some sense of where this blue curve crosses the x-axis. So let's do an AB line, a horizontal line with a y value of 0. Line thickness, let's do 2, and let's color it, or line type is 2, and let's color this black. Right, LTY equals 2 is going to be a dotted line. You can play around with LTYs to get other line types, right? So we see that the solution appears somewhere between 1 and 1.5. So if we use any numerical methods and we get something else, that is definitely not right and should not be trusted, right? So the method that we're going to use for solving this is going to be the uniroot function, which is in base R as well. So let's call the solution SOLN, and we're going to be using, again, the uniroot function, and this is going to be equal to the function f. We're going to be solving on the interval 0 to 2, and you have to put that in vector form, and that's going to give us, hopefully, a solution that's useful. So if we look at SOLN, and we look at the things that it returns, so notice that it says $root. So we just do $root of that value. We have 1.21, which is in between 1 and 1.5. So in some sense, this is reliable. So what I want to do is I want to plot this point on this graph, and hopefully it occurs where that dotted black line and that blue curve cross each other. And hopefully it works. So once we see that, we're going to plot on the x-axis SOLN root, that value that we obtained, y-intercept 0, and let's color it in a different color. Let's do dark red. Let's see, cx is equal to 1.5, that's how big that point is, and pch is the type of shape, like triangle, square, circle, whatever shape. Let's do 7 for the square with the cross in it. So notice that our little point goes exactly where that dotted line and that blue curve is. Therefore, this value of 1.2197 appears to be the solution to this original algebraic equation. But it's very important to keep in mind, for this particular unit root function, at least personally, I wouldn't trust this to more than 2 to 3 decimal places. Otherwise, you probably would want to write your own method in order to solve this, but 2 to 3 decimal places is trustworthy for this. The next problem that I want to look at today is a problem that's closely related to the one that we looked at last time. So notice that for this blue curve that we have here, we see that there is one solution associated to that equation, and it was located between 1.1 and 1.3. But if you grab this blue curve and it crosses this dotted black line more than once, then the uniroot function should not be used since it's only going to find one. So what I'm going to do is I'm going to use another method that is not found in the base package, and it's going to be found in the root solve package, right? So you can install that and include that library, and one of the functions in there is what we're going to solve for finding multiple intersections. All right, so again, what I'm going to do is I'm going to define some function f, and f is going to be, again, a function of x, and the function of x this time is going to be sine x over x. All right, so let's just get an idea of what this curve looks like, and let's assume that we want to solve this on the interval. Let's solve sine x over x is equal to 0 on the interval, let's go for example 0 to 10. All right, so how many solutions does this equation have? I don't know, but we're about to find out. So our function f is defined. Let's get a sense of what the curve looks like, so we know at least or have something to base the accuracy upon. So I'm going to use the curve function, again, f of x, and the interval I'm going to be looking at is again 0 to 10. And let's again look at this color in steel blue. Right, so there's our little wavy looking function. Let's put a horizontal line there, horizontal line of 0. Let's keep consistent, LTY is equal to 2 and color is equal to black. And that's going to give us our dotted line. So between 0 and 10, it appears to be that there's 3 solutions. One between 2 and 4, another approximately equal to 6, and another one close to, 9.4, 9.5, something like that. So we're going to be looking for 3 solutions, so uniroot is not going to be the function that we want to use here. So the function that we want to use here is going to be called uniroot.all. Right, so the uniroot.all is part of the root solve package, and it's going to have a similar syntax to the uniroot function. So again, the function of reference is going to be f, and then the interval we want to search is going to be 0 to 10, and that's going to return you these 3 numbers. So 3.14, it looks like pi, 6.28, maybe 2 pi, 9.42, maybe another multiple pi, who knows. Right, so once we have that, now we just want to plot these things on our graph, and hopefully those intersection points appear at least graphically. They should look somewhere to be accurate, so we can decide, should we trust it, should we not. So I'm going to plot a bunch of points on top of this graph. And keep in mind, SOLNS is a vector, not a number, right? So SOLNS, that's the x values we want to point. And then we're going to plot 0, 0, 0, the vector. But generally speaking, I don't know how long SOLNS is going to be, generally speaking. So what I can do to sort of generalizely code it, so I'm going to do REP for repeat, 0, how many times? It depends on how many values are in SOLNS, right? So SOLNS, the length of that's how many zeros I'm going to put there. Color, we're going to do dark red. And let's do the same exact format as before. So CX of 1.5 and then a PCH of 7. And once we plot that, notice that those points should cross at approximately the same exact location as our blue curve and our dotted black line, which they appear to do. Therefore, we should be able to trust these solutions, which are given to be equal to 3.14, 6.28, and 9.42, and generally speaking, trusting them to about 2 to 3 decimal places is usually a good place to keep in mind. And if you want more accuracy than that, again, you probably should be coding your own methods, but it at least is a starting point for the conversation. The next problem that we're going to look at is in some sense a generalization of the last problem we did and also the first problem we did. But now we're going to consider a systems of equations that potentially do not have the same amount of equations as unknowns, and it could have multiple solutions, right? So it's some sense a combination of the previous 3 problems. So the method that I'm going to be using here is going to be coming from the NLEQ SLV package, which you can of course easily install for free, right? And this is going to be used to help us solve nonlinear systems of algebraic equations, right? So hopefully we have some pretty curves sort of hanging out in 2D space, at least then we can graph it, but it can be used to solve higher dimensional things, but then you have a little downside of visualizing what you're sort of looking for. Right, so let's assume that the systems of equations that we want to solve is going to be equal to x squared plus y squared is equal to 1 for the first equation, which is of course just a unit circle, and then sine of x plus e to the power of x times y is equal to 2 for the second equation, which is, has a very interesting shape. Okay, so let's first off define our two functions. So f1 is going to be equal to a function of both x and y, and this is going to be equal to x squared plus y squared. Again, you're going to be setting this equal to 0, so we're going to be subtracting both sides by 1 there. And then f2 is also going to be a function of x and y, and this is going to be equal to sine of x plus e of x times y minus 2. So that is our second function. And now what I want to do, let's assume that we want to solve on the interval, let's say negative 0.2 to 1.2. Now, of course, I sort of know where the solutions are. That's how I'm sort of coming up with these numbers because, I've graphed it on a bunch of intervals, so I have some sense of where they are. But let's assume that you're told, the interval that you want to search for, negative 0.2 to 1.2. So I'm going to generate a sequence on that, and actually let's suppose that we want to solve on a square of the same exact size and range, right? So that's a nice little square, but you don't have to solve across that x times y domain, but it's up to you to decide. So we're going to be sampling our domain, so we're going to do a sequence from negative 0.2 negative 0.2 to 1.2, and we're going to partition that with 100 points along that domain. So we have a nice fine grid. And then we're going to have y, which is going to be the same exact thing, and let's assume that we have a length of 100. So that means we're going to have 100 times 100 points that we're going to be sort of evaluating inside of this two-dimensional square that we're going to be using to generate the graph of our potentially implicit curve. So once you have your domain partitioned, our first curve, which I'm going to call Z1, is going to be, so we're going to be using outer for this implicit curve, we're going to be doing x, y, and then f of xy. Keep in mind, x and y are now these vectors defined on lines 15 and 16. And we're plugging in all of those 100 times 100 numbers into this function fxy, right? And the function that we're going to be referencing in this first curve is going to be f1, right? So that is going to be what we're going to have for our first curve, and something doesn't seem to be right. This should not be a comma. Right? So that is going to give us our first set of points, and then our second set of points, z2, is going to be the same thing, so outer xy function of xy, and this function of xy is going to be equal to fx2. So what we're sort of doing is we're defining a function inside of this outer function, but we're defining it as f1. Now you may be thinking, can I just put f1 here instead of function xy, f1 xy? The function outer doesn't read it as simply as that, at least not in the current version of implementation. So this function xy is sort of needed here, even though we sort of already have it. Defines on lines 8 and 11 of the same exact code, but that is what it is, right? So that's going to be our z1 and our z2. And in terms of plotting this, we're going to be using the contour function. So x, y, z1, levels is equal to 0, aspect ratio 1 is going to be a nice square box graph, and then let us plot this in steel blue, just like we did the other curves, and that's going to give us the portion of the unit circle defined on negative 0.2 up to 1.2. So that's our first curve, and let's do it for the second. So contour, x, y, and z2. Levels is equal to 0, aspect ratio the same as above, and then we're going to do this also in steel blue, and we're going to have some other curve as well. Right, so notice that it doesn't show both graphs on the same exact thing, but you can easily do this with the contour by adding this contour to the previous contour by adding another command, add is equal to true, and that's going to add it to the previous contour. So if we do the circle first and then that value, it'll plot them on the same exact point, which is what we want. Let's draw our horizontal and vertical axes of our 2D plane. So AB line, H is equal to 0, LTY is equal to 2, color is equal to black. So that's going to give us our horizontal axis, and AB line, H is equal to, V is equal to 0 for vertical line, LTY is equal to 2, and then color is equal to black. That's going to give us our y-axis, so we can get some point of reference of sort of what we're looking at here. So this is our solution region, right? So how many solutions do you see? I see 2, right? Somewhere located about here and somewhere located about there. So let's see if we can find out where those are located. So for this, again, we're going to be using the NLEQ SLV library that we included at the very beginning, and the function that we're going to be using here is the NLEQ SLV function, which requires us to define the systems of equations directly as a two-dimensional vector. So how are we going to do that? So we're going to define a new function, and this is going to be of a single variable x, but it's actually not a variable x, it's going to be a vectorized variable with two inputs, x1 and x2, which is going to sort of represent our x and y. So this is just how our function is going to read it. So y is going to be a two-dimensional numerical variable. This is just required for the input. Our first variable, y1, is going to be equal to x squared, which is going to be x1 squared, plus x2 squared, which is y squared in this case, minus 1. And then y2 is going to be equal to sine of x plus e of x times y minus 2. Right? So that is going to be our implicit function that our function is going to need. Right? So let's use our NLEQ SLV function and see if it finds the correct solutions. So we're going to just plot the solutions on here. So NLEQ SLV, and it sort of helps us type there. And let's assume we want to use an initial condition. So if you know anything about initial conditions like Newton's method or bisection method or anything like that, it requires us to do an initial guess. So let's guess, for example, 0, 1, somewhere up here, and hopefully it converges to that point up there, about 0.5 for the x and 0.7 for the y, something like that. So this C, 0, 1, is our initial guess, right? So our initial guess of 0, 1. Okay, once we feed it our initial guess, then we're going to feed it the system that we want to solve, which is given by the function s. Now it's going to return a bunch of things, but the values that we want are going to be located in the first and second element, which is the x and y coordinates of our solution. So we're going to get our x value, and then we're going to get our y value. So just copy and paste that. So that's their x value, comma, our y value, right? And then we're going to, let's color this, for example, dark red. And let's do the same exact point structure, 1.5, PCH7. And that should, if I did everything correct, give us our solutions. Oh, I see what's going on here. I forgot to return the output y from this particular expression. So just go back up to that function definition of x and put s and put y at that last line of that definition. And let's just give that a rerun, and now it works perfectly fine, and it graphs our particular point of interest. And see, our initial guess of 0, 1 did converge to 0.5, but that's not the only solution. We need to use another initial guess to converge to the other solution. I think 1, 0 is really close to that point, so I'm going to use that as an initial guess. So initial guess of 1, 0, and I'm going to do the same exact thing as I did above, except I'm going to use a different initial guess. So instead of 0, 1, I'm going to choose 1, 0, and then 1, 0, and plot the x and y value that it returns, and hopefully it gives us that particular point. And those are our solutions. Now, if you're not exactly sure what those values are, you can of course, just copy and paste these values. So for example, here the x value for that first point is 0.48855, and then the y value of that first point is 0.8728. And then if we want to switch it around, for example, the x value of the second point would be 0.98, and the y value of the second point would be approximately 0.15. So that's how you can use the nonlinear equation solver package in order to solve nonlinear systems of algebraic equations, which is actually very, very useful in general problems. The last problem that I want to look at today in terms of solving equations in the R language is how to find lower or potentially upper quartiles of general continuous probability density functions, which, if you know anything about, requires a bit of integration in order to find, especially if it doesn't have a closed form antiderivative, which can get a little bit messy. So what I want to do as an example is work with the log normal probability density function. It has a lot of applications. There are some packages out there that already have this implemented, but I want to sort of show you how you would go about it in case you are working with a probability density function of your own that you potentially created, but still need to do the same exact thing. All right, so let's get started by building our probability density function. So for a log normal probability density function, usually you know the median and the mode of the distribution. Let's assume, for the sake of example, the median is 5.4 and the mode is equal to 4.2. Let's assume that those are the two things. When I did this in probability in our video, I used the same exact example as this, so I'm going to use it here for consistency. Right. So for the parameters of the log normal, which I sometimes abbreviate by A and B, some people will use mu and sigma, but I don't think that's a good notation. A is going to be equal to the natural log of the median. LOG by default is the natural log. And B is going to be equal to the square root of the natural log of the median divided by the mode. Right? And keep in mind, for the log normal distribution, median is always bigger than the mode. Once we have our parameters A and B defined, now we can define our probability density function, which I will denote by little fx. I'm going to be using capital Fx for another function, so I recommend not using capital F here in case you wanted to change it. So this is going to be a univariate probability function, so just a function of x, and the PDF is going to be as follows. 1 divided by x times b times the square root of 2 times pi, close parentheses, times e to the power, so exp, of negative 0.5 times, open, natural log of x minus a over b, the quantity squared, and close, and that is going to be your probability density function for the log normal random variables x. Okay, so once you have our PDF defined, now what I want to do is construct a graph of this probability density function. And let's create a nice discrete graph on a very fine domain with domain partitions of size 0.01. You can make this smaller if you want, but usually it's going to take up a lot more space in memory. So once you have decided on your delta x value, we're going to then create an x domain that we want to span across. Let's assume we want to go from 0, but this is approximately equal to dx in this case, to 35, let's say, and let's increment by dx. Now, there is a question here, why 35? The domain of log normal is 0 to infinity, but why do I only go up to 35 for this case? I'll come back to this in just a moment to sort of guide you on how you can choose what that upper bound is going to be, because we can't go to infinity because then our vector is going to be infinite dimensions, and we can't handle that, at least in the current level of computational power. All right, so if that is the case, let us plot our curve. Let's plot our x values on the horizontal, fx of x on our vertical, and then pch of 16, that's going to give us some small circles, cx of 0.5, and then color is equal to steel blue. right? So that is going to give us the graph of our probability density function. Now keep in mind the highest value here is approximately like 0.18 or something like that. But what I'm going to do is I'm actually going to change the height of this curve. Remember, the only thing we're aiming here is the percentiles of this distribution, and percentiles range from 0 to 1. So what I'm going to do is I'm actually going to change the height of this curve so I can overlay the cumulative density function on top of the probability density function so I can sort of connect the two together, at least on the conceptual sense. Because keep in mind, although we're going to be graphing something that is not exactly f of x, it's going to have in some sense the general shape, but all of our percentiles are going to be calculated based upon fx, not the thing I'm going to plot here. So as long as you keep track of what you're doing, everything is okay. So what I'm going to do is I'm going to divide this by the maximum value of that function. So I'm going to divide by the maximum value of fx of x, and that's going to make the maximum value of this graph always equal to 1. And as you can see, it does exactly that. So once I have that there, notice that in this particular graph, I do have a bunch of points that are sort of very close together. Some people will connect these with lines if you are choosing, for example, a bigger dx value. So let me just show you sort of what that would look like here. Notice that you have a bunch of points here. If you want to connect them with lines to have a nice smoother looking curve, you can do, for example, lines of the same exact input. And it's going to connect all those points with lines, right? But in some sense, for our example, we have delta x is 0.01, which doesn't necessarily need the lines, but they're there hiding underneath our points. But that's up to you if you want to include them. So let's introduce a horizontal line of 0 and a vertical line of 0, just sort of get a point of reference. So AB line of horizontal 0, LTY equals 2, color is equal to black. It's going to be our horizontal axis there. And then AB line V is equal to 0, LTY equals 2, color is equal to black. That's going to give us our vertical y-axis there. Gives, again, to give us some base reference. So, in this particular picture, the area underneath the entire probability density function from 0 to infinity is equal to 1. But notice that we're going up to 35, so we should hope that the total area underneath our discrete or our discretized domain value for our PDF is as close to 1 as we could get, like 0.9999 from 0 to 35. So this is where that 35 is going to come into play. So to check that you have practically 99.99% of your data from 0 to 35, what I'm going to do is just numerically integrate the function f of x from 0 to, well, let's actually go up to 20 to sort of see what it's going to do there. And notice that we have 0.9955, which is not close to 1. So that's why I chose, for example, 35, because it gives me 4 nines. Obviously, you can go up a little bit larger, but if you only seek, for example, to have a 2 decimal place accuracy, that should be relatively sufficient as long as you don't have anything crazy going on above this particular value for the domain. But one can show that the log normal distribution is monotonically decreasing after 35, so nothing crazy going on down in the domain beyond 35. So once I have verified that this definitely does cover the majority of the domain, or in some sense the majority of the support of the probability density function, as some fancy people say, now we're ready to create our cumulative density function, which I'm going to abbreviate by capital F of x. Right now it doesn't have any values, so I'm just going to define it as a blank vector for now, and then we're going to slowly add on all the values as we integrate from the lower bound of our domain up to every single point of our domain that we have calculated. So we're going to do every single integral from 0 to every single point in our domain vector x, right? Which is the definition of a cumulative density function. So to do that, I'm just going to do a for loop here. So let's do for k in our domain vector x, and let's first calculate the integral. So we're going to integrate the function f of x, lower minimum value, which is dx in this case, but this is a little bit more general, upper value, whatever k value we're at, and then we're going to have fx is equal to append fx, the value of that particular integral. Right. Now, just a couple notes here. You can try to put this integral inside of this append, but it's not going to work, at least in the current implementation of the thing. And the actual return of integrate is going to tell you the value and a couple of the error bounds that it's sort of calculating it. For example, when we did, for example, the integral of fx, notice that it gave us some other stuff here. We don't want that. We just want that area located right there. So that's what the $ value at the end of val is actually doing there. Right? So that's going to give us our cumulative density function, capital F of x, and now what I want to do is graph that on top of our normalized probability density function. Right? So I'm going to do points of x and then our fx, and keep in mind that's a vector now, not a function. Again, pch is equal to 16, cx is equal to 0.5. Let's choose a different color. Let's choose coral. Right? And that's going to plot our cumulative density function. If you remember any theory about CDFs, it is always an increasing function, so it should never go up and then down. It should always be increasing. And of course, you can connect those dots with lines if you have a bigger dx, but I'm not going to do so. Let's do a horizontal line of y is equal to 1, because that's the upper bound of every CDF. So LTY is equal to 2, and then color is equal to coral. Right? So this is our PDF in blue, our CDF in coral, right? So now we are ready to find any percentile, at least rounded, of this log normal probability density function, right? So by default, it's going to try and, for example, if we look at this fx thing, notice it does a lot of scientific notation things. What I want to do is just turn that off because it's really hard to see. Turn off scientific notation, just set scipen is equal to some really large number like 999, and then it's going to give you everything in decimal form, right? Which is what we want to look at. So now we'll want to find, for example, a particular percentile. As an example, let's look for the lower 80th percentile. The 80th, not the 8th, but the 80th percentile, which is the upper 20th percentile, right? So 80% of people are below this number, something between 0 and 35. Because keep in mind, about 100% is between 0 and 35. So 80% of people should be below some number here, and 20% of people should be above that same exact number. That's the number that we're looking for here, right? So what we can do, what I actually want to do is I want to create a horizontal line. So let's do AB line. H is equal to 0.8 because that's the percentile we're looking for. LTY is equal to 2. Let's do a color of dark red. Dark red. Right, so there's our 80th percentile line. So we need to find the value of x for which this orange curve crosses that dotted red line, which appears to be somewhere around 8 or 9. Right, so that's going to be our lower 80th percentile, aka upper 20th percentile. So what I can do is I can shift this entire orange curve down by 80%, and then that point of intersection is going to shift down to the horizontal dotted line, which is, y is equal to 0. So in some sense, we're going to be looking for the x-intercept of the curve f of x minus 0.8. But when we move that coral curve down, we're going to have all of these values as negative y values and every value above as positive y values, right? But if we take these values here, which are now negative, and then mirror them up, you're going to get sort of a graph of a bird, right? Where the value closest to 0 is now going to be the minimum of that bird curve. So instead of defining v as that, what I'm actually going to do is I'm going to look at the absolute value of all of those curves there, right? And this is actually going to be an interesting curve, so I'm actually going to graph it just for fun. So I'm going to graph xv And let's choose a different color, for example, dark green, right? So there's our V, let's plot that. And then you're going to have this interesting curve here. So this value, this minimum value of the green curve should be at the same exact value as approximately the intersection of dotted red and orange. So we're just going to find the minimum value of V, and that should be an approximation for the 80th percentile, right? So x 80th percentile, at least approximately, is going to be a particular x value, which one? The value for which V is minimal, which you can do with the which function in that particular scenario. And if we look at that value, we get a value in between 8 and 9, which is what we conjectured in the very beginning. So let us just plot this value on that orange curve and see if it crosses at approximately that point, right? And hopefully it does. So let's do an AB line, vertical at x 80p, LTY is equal to 2, color is equal to dark red, and that's going to give us some vertical line, and it's going to cross there. And now we're going to plot those values, and hopefully they do cross, and they should because we've already found them. And these lines are based upon those values. So ADP, 0.8 for 80th percentile, COL is equal to dark red, CX equals 1.5, and PCH is equal to 7, and this point should be approximately equal to there. And since that's where those lines cross on that orange curve, then we have evidence to believe that, at least approximately to 2 decimal places, the 80th percentile is approximately 8.23, 8.22, 8.24, somewhere around there, right? And that is one way you can find percentiles for arbitrary continuous PDFs using base R, just using some basic integration methods. So those are some very, useful ways in order to solve a bunch of different types of equations for a variety of different types of purposes. Of course, there are some other equations we didn't discuss today, for example, differential equations and integral equations, but I will introduce them at another time if necessary. So I hope you enjoyed this video, and I'll see you then. Take care.